So question number 8 on page 113 says that a spring constant of 150 newtons per meter is compressed by 4 centimeters. The spring is horizontal and the mass of 1 kilogram is held to the right end of the spring. If the mass is released, what speed will it move away with? So if we think about this situation, again, I like to draw our pictures, right? And we'll draw two different pictures of one. We'll have this be kind of the natural length of the spring with our 1 kilogram mass there. And then our other one will be with our mass compressed 4 centimeters. So that's our displacement from kind of the normal position of 4 centimeters. So that's 0.04 meters. And what we can think about is what's going to happen is there's going to be some force pushing this way on the spring or due to the spring. And otherwise, besides that, we're also going to have the force of gravity and the normal force on our mass. These two forces, the gravity and normal force, would cancel each other out. And really the one force that we'd be dealing with is the force of the spring, as long as there's no friction. So if we were to look at that, our sum of the forces in the y direction would be our normal force minus the gravity equals mass times acceleration. Our acceleration is going to be 0, which from that then we can figure out that normal force and gravity would be the same. Otherwise then in the x direction, we're going to have the force of the spring, and that's going to equal mass times acceleration. So what's going to happen is as our spring goes from here to here, there's going to be some acceleration to the right. And so once our object gets back to this equilibrium position, we're going to be moving to the right. And what we're trying to figure out is what is the speed that that's going to be moving away with. So we're going to do two different methods to do that. The first way I would say is the more common way, and that's going to deal with energy. So find velocity of our mass after the spring pushes. And again, our first way is we'll use energy to think about that. And then the second way is we'll use the idea of work, and hopefully we should see that both of those are going to be the same result. So if we think about this, in this situation, we're going to have elastic potential energy of the spring. That's going to be some value greater than 0. There's going to be no kinetic energy, and then there's no gravitational potential energy here either because it's at a height of 0. Now again, this is not higher than this. This is just, it goes from here to here. But here now we have some kinetic energy, which is going to be greater than 0. And our elastic potential energy of the spring has now become 0 for the fact that we're now at this, uncompressed or unstretched position, or equilibrium position. And so all of this stored energy in the spring here has now been transferred into our 1 kilogram mass here, and we can then figure out the velocity. So to do that, we're going to say that the elastic potential energy of the spring to begin with has to equal our kinetic energy of the mass afterwards. So that's going to equal 1/2 k delta x squared. It's going to equal 1/2 mv squared. Now a nice thing is that our 1/2s go away. And I'm solving for v, so I'm going to divide each side by mass. And what I would get is that v squared equals k delta x squared over m. And then I just need to square root both sides. And I'd be left with that the velocity is going to equal the square root of k delta x. Oh, actually, you know what we can do? We can pull one of this delta x squared out. So let's redo that. And so this would be, that would be delta x. and then the square root of k over m. Plug in our values then, 0.04 times 150 divided by a mass of 1. And that's going to give me a velocity equal to 0.49 meters per second. Oh, excuse me. Meters per second. Okay, so that's dealing with the problem using the concepts of energy and the fact that whatever the energy was to begin with has to equal the same amount of energy at the end. So my elastic potential energy turned into kinetic energy, and then I can solve through it like that. So again, let's do the same idea, but this time we're going to use work and try to solve the problem with that. So in the same method, so let's deal with this problem using work. So how I would do that is similar to what we did in the previous questions, where let me redraw this so we can think about this. So here's my spring, here's my starting position, and then it's going to push it until it reaches here, we'll say. And so that's my equilibrium position right here. So this is x equals 0. And then again, this has a displacement of 0.04. So we can think about this in terms of there is some force of the spring pushing this way. And then here, at this point, the force of the spring is 0, because remember, using Hooke's law, our force of the spring is going to be kx. And so what we can find is we can find the initial force of the spring, which is going to be 150 times 0.04, which is going to give a force of 6 newtons. The final force of the spring would be 150 times 0, so that would be 0 newtons. So the average then, the force of the spring average, would be force initial plus force final divided by 2. So that's going to give me an average force of 3 newtons. Okay, so then what we can understand is, again, we can understand that work equals a change of kinetic energy. And for our initial situation, the kinetic energy is going to equal 0 because it's not moving. And then for our final situation, with the block moving to the right now, we have some kinetic energy greater than 0. So if we can find the amount of work that's done, we should be able to find the change in kinetic energy, which, if I write that out, that's going to be kinetic energy final minus kinetic energy initial. Again, our kinetic energy initial is 0. So this just becomes work equals the amount of kinetic energy that I have at the end. We know that work is force times displacement cosine theta. And we know that kinetic energy is 1/2 mv squared. So if we look at that, some things that we need to understand. One is that my theta, in terms of the direction of my force and the direction of my displacement, that's going to be 0. And that's going to make this whole value just 1. So then this becomes the force times the displacement equals 1/2 mv squared. And again, we're going to solve for v. So what am I going to do over here? I'm going to divide by 1/2 m on both sides. Again, this would be my average force for the entire time. And that's then, I'm going to write it over here, of v squared equals 2 force times displacement divided by m. And then we're going to square root both sides. So that becomes the velocity equals the square root of 2 times my force average times my displacement divided by my mass. And hopefully when we plug in the numbers, we should get the same velocity that we did before. So plugging in 2, my average force is 3 newtons. I have a displacement of 0.04 divided by my mass of 1, not 7, but 1, and then we're going to square root that. When I plug that in, I'm going to get a velocity equal to 0.49 meters per second. And so again, it doesn't matter which method we use, which is the beauty of energy. And it can sometimes be confusing, the confusing part in that if we understand, the energy initial equals energy final, we can do that method. Or if we simply use the idea of work equals a change of energy, we can do that method. Both of them produce a final velocity of 0.49 regardless. So those are 2 different ways that you could work through that problem.